Good morning, everybody. Last week, we started talking about file systems. Today we will continue on it. We said that the disk, the secondary storage, is a very simple very simple device conceptually. Physically, hardware-wise, it is complicated, but logically, it is very simple. All you can do is, from the whole disk, read block number K and write to block number K. That's it. Okay. So a disk is divided into blocks, and the size of the block changes from system to system. Some systems take this block size as one byte, so you read it one byte by byte. Some of them are like 12 bytes, some of them are 1 kilobytes, and etc. But all you do is disk is a linear space logically, and you read block number K and write to block number K. So this is so simple. Why do we need to make an abstraction on it? But this is very similar to what memory is, right? Memory is very simple, but we had to spend more than a month to explain why we need to abstract the details of the memory away, so that we can do the multiprocessing, we can do the protection, we can do loading of multiple programs, and etc. The same is valid. We need to abstract this a linear space of blocks as secondary storage, and the task belongs to the operating system again, and that's what this chapter is about. So let's continue then our discussion on the files. So these basic two operations, but we are going to introduce many things, right? Okay, make it easy for the user to find their information. Okay, provide protection between the users. I mean, I should not be able to read the system's data, or I should not be able to read or write to other users' data, or there should be management. Remember the task of the operating system, abstracting away the details of the hardware plus the management of the resources. So how do I manage the free storage on the desk, and etc. So I need to answer these kind of questions, and all I can do is this: read block number K and write block number K. So it is very similar to what the memory is doing, and the things that we are going to do is going to be very similar to what we did with the memory actually, other than we will not have anything like paging or something like that. That will be different issues. Okay, so last time we started talking about that. So how do we organize data on disk? So we come up with this notion of files. Okay, file is our answer to these abstractions, like the paging is the answer to many of the memory related stuff. File is the answer to is the solution to many of the problems that we are going to face. So they have invented the file. A file belongs to a user, and it is again linearly addressable. With a block K for reading or writing, and block could be as small as a byte. Okay, so you open a file, you create a file, you open a file, you write to a file, you append a file, you close it. Those are the operations, so those are the defined stuff. But then there are some design decisions, like what could be our file names. Okay, how do we organize the files? Where do we keep them? Okay, what are the access privileges for the files, the versioning of the files, fault recovery, etc. Okay, so and last time we started talking about the files and file names. We said that okay, the rules for the file names very much depends on the operating system. Some of the operating system file names are case sensitive, some of them are not, and some of them let you use any type of characters. Some of them will tell you that no, only the ASCII characters are allowed. Some of them say that I will allow the extensions, and in fact I will require the extension. Extensions are important for me. Some of them say that okay, you may use the extensions, but I don't care what the extensions are. Extension for me is nothing more than a regular file name, etc. Okay, so these are the differences, and usually these are defined by the operating system, and the users are users let known are let known about the rules of the file names. And then we have file systems, how we organize the files on the disks. Okay, it is an important part of the operating systems. Okay, important part of the operating systems is the part that deals with the files. Okay, and we will talk mostly about the file systems, and these are some different file systems. Okay, so the meaning of file system is this: how we implement the idea of the file on a disk, on a secondary storage device. Okay, how we implement them on a secondary storage device. This could be your disk. Okay, this is your disk, and you divide your disk into tracks and sectors. So each concentric ring is a track. For example, this one is a track. Okay, within the tracks are divided into sectors, and in the sectors you have the blocks. Okay, so this is how the disks are physically arranged. The users doesn't know about these. Okay, and a file system takes this structure and it says that I am going to see this whole disk as a linear space of addressable positions, and I will put my free block list into this position, and then my internal data, sometimes I need into this position. The rest of them will be my files, etc. So you need to make these kind of decisions: where you keep your files, where do you keep the information about the files, how do you structure your files, your directory structure, etc. So these are all decided by the designers of the file systems. Okay, from the beginning always we had the file systems. Some of them were very primitive, some of them are very sophisticated. One of the most widely used file systems is FAT16 MS-DOS file system. Okay, what is the meaning of 16 and 32 will come later. The meanings of those two numbers will come later. Basically they are the addressable space. So this can address 2 to the power 16 blocks. This one can address 2 to the power 32 blocks. Okay, this is like again, like very similar to memory. Remember 32-bit computers and 16-bit computers. It's similar to that. Okay, so the FAT16 is a MS-DOS thing. So since 2 to the 16 is not a very big number, later they made it FAT32, and Windows 98 started using it. But there are many shortcomings about these file systems. So they invented this NTFS in the Microsoft side. Windows NT uses NTFS, okay, NT file system. And then for the newer operating systems, starting from the Windows 8 and different versions, you have the resilient file system. That is, it does the journaling. Okay, it has a very good answer if the system crashes while you are doing something on your desk. So it always knows that what it did and what it didn't do. So it has this journaling property. And similarly for the removable media, we have exFAT or large file systems, and we have similar file systems for the Linux side, Unix side, Macintosh side, and some of them are compatible with each other, some of them are not, and some we will talk about them. But basically, we will talk about the basic structure, how you keep your files on your desk and how you keep your um, empty nodes, how you structure them. Okay, good. Remember, we talked about these in the memory discussion, how you keep your empty pages, uh, uh, how you keep your how you keep your data protected in the memory. And the same discussion will come, but since the environment is different, the problems are kind of different. Disk is so slow compared to memory. Okay, this is so slow compared to memory. So we have enough time to make some expensive processing before we access to the disk. We have access the disk. Why? Because doing something in the memory compared to disk access is negligible. That's why we can afford to do some processing before we access the disk. So that will be the main difference. Since we have this in our hands, we can take advantage of it. We can take advantage of the disadvantage of disks being slow. Okay, good. For the file naming approaches, okay, these are some of the extension stuff, typical file extensions, and you know most of them. And as I said before, file extensions are not important for some operating systems. For example, for Unix, doesn't mean anything. Remember what I did last time? I showed you how you okay. Okay, when I say give me the file types of all the okay, give me the file types of all the stuff in this directory, it tells me what they are. And if I modify, see this one here, I modified it so that the extension is something stupid, and the Unix doesn't care if the extension is something that it had never seen before. Okay, it still says that this is an executable code. Okay, it knows everything. Okay, how about this one? Test.cpp to test.java. Does it work? See, it says that it's a C source, even though it has a Java extension. It looks at inside and it makes the decision that way. Okay, good. So, uh, extension doesn't mean much for the Unix environment, but it is important for the Windows environment. And these are some of the standard extension names. Usually, but even though for the Unix environment, extension doesn't mean much, but it is permitted and it is meaningful for the users. I know why. I know what Java means. I know what CPP means, and as a user, I use that information to understand stuff, to remember stuff. Okay, so let's look at this file structure. How the files are kept on the disk. Okay, so what is a file again? File is a linear space. It's like a segmentation idea of the. It's like the segmentation idea of the um, memory. Okay, each file is a new segmentation. If each file is a new segment, you ask the operating system, okay, give me a new segment on the disk, and it gives you a segment on the disk. Okay, so that's it, and you access your segment the way you want. You add data to it, you remove data from it, you append it, you erase it, etc. Okay, so how on the disk, how these files are structured. Okay, on very old systems, okay, everything meant was the records, and initially the records are images of the punch cards. Remember those punch cards? I showed you the punch card, right? It's an 80 column representation of the data. Okay, it's called punch cards, and on all systems the files are organized that way. Okay, record is a collection of bytes, The record size is 80 characters or 512 characters or 1 kilobyte, doesn't matter. So each file is composed of records. If this is your file, okay, each file is composed of records, and the length of the record, okay, length of the record is fixed for that file. Usually the length of the record is kept inside the file attribute information or file metadata. Okay, and as the slide says, initially each record corresponds to a punch card. Each record corresponds to a punch card. Later for Unix and from Unix to Windows, okay, file means for Unix or Windows, file means is a byte addressable linear space. This is byte number 0, this is byte number length of the file, whatever it is. Okay, so you just say that seek to that position. Remember the seek function of C. Okay, you say that open this file, seek byte number 10,1200, and I am reading from there. Okay, I am reading from there. Some systems they have page-oriented file systems. Okay, it's like the records, it's page size blocks, depending on the system. So we mostly in this chapter we are going to assume that we will have byte addressable structure of the files. This is how the user sees them, of course. But at the end, if you have a mechanical desk, your data is organized this way. Okay, your data is organized this way. You have your tracks, you have your cylinders, you have your tracks, and you have your sectors. And we are going to look at this structure later. But for the user of a Unix or Windows operating system, a file is a byte addressable linear space. Okay, just to give you some idea of how the other things work, this is the idea of the Unix byte sequence for a file. So for other systems, it's a collection of records, and this is again another one. This is a collection of records again. This is your complete file, and I think in 1960s, Apollo computer, I think it was organized this way. They kept their files in an ordered way. Okay, if you are keeping animal names, okay, in your file, this is how it is kept in a hierarchical structure, and hierarchical structure, and it's like B tree. You know B trees, right, from your data structure course. What is the advantage of keeping your data this way instead of this way? What is the advantage of B trees?
Searching is fast.
Searching is faster, yes, definitely. Searching is faster. But I think you could do the same kind of searching with this. If you say, I have this many bytes, you would do, if, I mean, this is ordered, right? You would make a search using a binary search, right? I mean, if you keep things sorted, you could make a binary search. So what is the advantage of it?
I think it's having multiple, like not just binary files, but multiple files, more than two files on each stage while maintaining the log n property.
You are saying that each record could have different size. Is that what you are saying? You mean each one has a different size?
we have a normal binary tree, we could only have just two files on each stage, so that wouldn't be convenient. The layers will be a lot more, and searching, even
You
if
mean,
it's a
yeah,
binary
okay,
tree, it
okay.
will be.
So this is like 2, 3, 3, and you don't have that many levels with this kind of tree structure. Well, at the end, all we are going to do is represent them like a linear space. Yeah, that could be it, but there is a bigger advantage with these B trees. One is searching is faster, yeah, searching is natural. You search it very, very fast way. The second one is what? Second one is it is insertion and modifications are much easier. I mean, if I need to insert a new animal to this tree, okay, again, it's a log n time. If you like to insert something to this tree, to this data structure, linear space, you will need to do it's a linear time, right? You will need to do lots of pushing data over. So, but again, you can represent this kind of stuff using the 1 byte representations, and we don't use this. We don't use this. We let the user have this kind of a file representation and do whatever they want with by means of libraries. Okay, for the operating system, we are talking about the operating system. What kind of files we have? All the files are addressable like this. That's our assumption, okay? But again, even though they are addressable like this, there are types of files. Regular files is the ones that are useful for the end users, okay? Directories are files, but they are special files. Why? Because they keep information about other files in them. Okay, directories are files, but they are special files in that they keep information about other files in them. Okay, there are character special files and block special files. Okay, the idea of the abstraction of the file can be modified in a way that your file is connected to, for example, the keyboard. Okay, whatever you read from the file, actually you are reading from the keyboard, or whatever writing to a file, you are actually writing it to the terminal. Okay, so these are the character special files. Okay, they look like file, but they are actually not represented on a disk. Okay, they are connected to a physical device such as the keyboard or the network or the printer, and you read from these files. The data doesn't come from the disk, data comes from the special device. These are called character special devices, and again, we are using the abstraction of the file to represent the data in a different way, to represent the data so that for the user the interface is more uniform. To be able to interact with the terminal, all you need to do is just open a file and read the file, and in fact you are reading it from the keyboard or the network. Okay, doesn't matter. Okay, these are called character special files, and there are block special files. Okay, they are used to model disks, but usually we will not talk much about these type of files or these type of files. Okay, for the operating system these two exist, but usually we are going to talk about these regular files and the directories. Okay, so depending on the system, okay, a regular file could be formatted in a different way. Okay, for example, for the Unix system, this is the structure of the executable file, and the structure of the executable file is different for different operating systems. Okay, so at the beginning, for the Unix operating system, at the beginning of the executable file, there is a magic number, some stupid number, 0xf2b717. Okay, remember that file command that I show you? File command, when I say file something, okay, it reads the first few bytes, and if it sees these numbers in there, it says that okay, this is an executable file. That's what it is. Okay, that's how it decides it. Okay, then after that you have the code size, the data size, BSS size, symbol table size, etc. And at the end I have the entry point. You find the entry point. This is the point where you will start your execution of this executable file. Okay, again, this is very specific to the operating system. In fact, for the Linux operating systems, I think this is specific to distributions too. So the binaries of different Linux distributions are different. That's why when you try to download a binary for Ubuntu or Fedora, you have to download different binaries. Okay, so the files are structured differently for different file types. And again, this is a structure of an archive file, a zip file, for example, or tar file. I think tar file is a better description for this one because this is not compressed. This is just you put different modules one after the other one. At the beginning you have the header, okay, and in the header you define your owner, your protection, date, size, and etc. And then you have your object module, another header, another object module. So you put them one after the other. So by looking at the size, so you first know the size of it, then you get the size from here, the second one size, and the third one size, and etc. Let me do it better way. Okay, so as you see, the object modules, size of the object modules are different. So, okay, good. So the structure of each regular file is different. An operating system knows it. And you know this, the files could be accessed using sequentially or random access. Okay. Um, for the sequential access, you start from the beginning and you read your file byte by byte or record by record. Okay. You are not allowed to skip beginning of the file. So if you need some data from the middle of the file or end of the file, you need to read the whole file. These are the sequential access files. As opposed to sequential access files, there is random access files, and you know what they are. You can do sequential access or random access like an array. Okay. For Unix environment or the Windows environments, we don't have the sequential access most of the time. Sequential access files existed usually for the tape drives, because for the tape drives, not the disk drive, for the tape drives, this is what you can do because there is no seek head for the tape drive. Okay, good. And for each file, there is associated attribute fields, or sometimes they call them metadata. Okay, so what are the attributes? You like to keep more information about the data. Files store data, yes, that's true, but how about the data about the data? Okay, for example, the date and time the file was last modified is an attribute. Okay, this one, test.cpp, keeps a C++ file, okay, C++ source code inside it, so it keeps its data. But what do I do with the data about this test.cpp? So like who is the owner of this file? What are the access privileges, reading, writing, execution? Okay. When did I create this one? When did I access it last time? So these are all called attributes or metadata. An operating system again is responsible for um, is responsible for keeping this information. Keeping this information. Okay. So some of the examples about the metadata about the files, protection of course, who can access the file, in what way, reading, writing, execution, etc. Some files are password protected. I need the ID of the creator who created the file. Creator and owner are different. Okay, one person might create it and it is owned by somebody else. If this file is a read-only, files might be hidden. Okay, so regularly you don't see it, it is hidden. If you are the system or if you are privileged, you can see it. Some files are specific for the system. For example, the swap files that we talked about in the memory section, they are system files. There are archive flags, okay, some backup files. Sometimes for some systems they mark their files as ASCII files or the binary files. For Unix or Windows operating system, we don't have such a thing. Some files are sequential access, some files are random access, okay. There are some files that are temporary. Operating system or somebody else, okay, they don't use these files to keep their information for a long time. It is just temporary files, okay. Lock files, okay, 0 for unlocked and non-zero for locked files, like the mutexes, right? So lock files are the corresponding version of the mutexes in the file world, etc. So not all not all these attributes exist for all type of system. For example, you don't have this one or this one or this one or this one, okay, for Unix or Windows environments, okay, and their representations are different depending on your system. Good. Okay, these are the file attributes. Okay, the important thing is file attributes are the data about your data or file, and these have to be kept somewhere on your, of course, secondary device. Sometimes they are kept in the same file, sometimes they are kept in different places, and again, these are all design decisions, and we are going to get them later. Okay, so these are some of the familiar file operations. In order to use a file, remember what's a file? File is a sequence of bytes, a linear address space on your secondary device. You could say a file is your segment on the desk. Remember the segments? You may have as many segments as you like, practically, okay? And files are the same thing. You may have as many files as you like, practically, okay? It is as long as your disk space is sufficient, okay? You need to make a new segment, okay? You ask the operating system to give you a segment and you may return it, and etc. It is almost the same thing, okay? Remember, what was the main advantage of the segments? What was the main advantage of the segments in memory as opposed to paging? So you guys are you are allowed to go back and read your notes. Mehmet, are you saying something?
So maybe it helps to management.
Yeah. So explain it a little bit. That's true, but
So segmentation is a small units. So we, for example, we are not searching to all memory. So we just look at the small segments, maybe.
well, each segment keeps related information. That's true, but there is more than that. There is a better advantage for the segment. Remember, for each program, you could have a data segment, okay, code segment. Maybe remember the example of the compiler symbol table constant table, my temporary heap, and etc. So each segment holds a specific information. And sometimes we say that why don't we keep our shared functions in a different segment each? So this is my open function, this is my close function, this is my sum f3. So each function has its own segment. So it is very easy to share these segments between the processes. That's what we said. But what is the advantage of it? The advantage is I can grow and shrink my segments. As a user, I can grow and shrink my segments without moving around my data. Okay, I say that okay, I'm growing this segment, I am shrinking this segment, and operating system is responsible for providing the space. The same thing is here. Okay, I can say that I asked operating system, give me a linear space on disk, and I might make this file very, very large or make it very, very small in the future. So I don't care what you do on the disk. You are going to provide me this functionality. So the idea is very similar to segmentation. Of course, the pure segmentation implementation was difficult. So what was their solution? So how did the operating system manage the segments on the memory? What was the solution?
Maybe give the file a large space.
No, I'm talking about the memory management. Mohammed, I am talking about the memory management. Well, how did the operating system manage the segment in memory? Nothing. So what homework did you guys have this weekend? Last time you had a homework. So Usama, where are you? What did they tell you? Usama, are you there? I can find you easily. Oh, Usama is not in the lecture. So you need to tell me, so how did we solve the management of the segmentation issue with the memory? Okay, I will pick somebody random. Okay, I am picking Miray. Miray, are you there? Miray Yıldız.
Yes.
Okay, you are there. Good. So, just tell me something. You don't have to know. How can you grow a segment in the memory if you don't have? I mean, the user asks you to grow your segment. You are the operating system, and you need to grow the segment. How would you manage this one? The one thing that I can tell you, you can relocate all of your segment to a new space, but that is inefficient.
I don't know it.
Sir, in the question you're asking, is there any space left, any blank space, or is it completely full?
Well, that's part of the question. I mean, if the memory is completely full, you need to do something if there is space, but the space cannot be, if this is your memory, the whole memory, okay, this is your segment number 1, segment number 2, there is some maybe empty space, and segment number 3, and some empty space, segment number 4. Maybe it is easy to extend or grow segment number 3 because there is space. But it will be difficult to grow the segment number 1, right? So how would you grow segment number 1? You move the segment number 2 to some other place and grow it. but we don't like it because this one requires compaction and there is an external fragmentation problem. But there was a much better solution for the segmentation, growing the segment size or making it smaller. What was the solution? What was the solution?
Maybe get all the free spaces and put them near each other. You said that is the efficient.
So you are saying that we can grow some of the segments but cannot grow some other segments?
No, like just put all the free space near the segment we want to grow.
So how you apply your solution to this S1? How do you grow S1? I have free data, free space here, and free space here.
You have to shift the other spaces.
So you are going to do compaction, but I don't like compaction. I don't like compaction because it will take time. I don't understand. I asked this question like maybe 5 minutes ago. If I ask this question in the quiz, at least 30% of the people would have pasted the Wikipedia answer to this one, and yet nobody's answering me right now. The answer was paging. Okay, you page each segment. Okay, you page each segment, and what is the advantage of paging? The pages don't have to be contiguous. Okay, because each page, this is your page table for a segment. In your physical memory, each page might correspond to a different position in the main memory. So when you grow a segment, you add more pages to your segment table, the page table of your segment. And in physical memory, you don't care about the compaction. Okay, and the files are going to do almost the same thing. Okay, when you grow a file, your file doesn't have to be contiguously represented. Okay, so these are some of the file operations. These are some of the file operations that we already know from our programming courses, of course. We create files, we delete files, we open files, close files, we read from files, we write to files, append, seek, attributes, and etc. Okay, so question here, I have two questions. Why do we need to open a file to read it from the file? Why don't we say, remember, what was the function read? Read says that read a file descriptor, a buffer, right? And some length. I think this was the prototype, or this was how you use the read function. You give the file descriptor, open file, okay, you give the buffer and you give the length and it reads it. Why don't we do this? Read, okay, /user f.c and read me this buffer and read me 100 characters from it. Why don't we use this? Give the file name directly so that I don't have to open it.
Well, there's a case of a file that can be opened successfully or not.
Well, in that case, read returns a minus number, right? I cannot read it.
Yes, it is.
Yeah, so whatever that open gives you, you may return the same code from read. Why do we have to open it? Why do we have to close a file? Why do we have to open a file and why do we close a file? Just give the file name directly and read from it, or do that
So
kind of.
maybe because when we open the file, we load the information of the file from the disk to the memory. So we do it just once. If we do it like you said from the read function, we have to do it every time we read the file, maybe.
Exactly. Yeah, exactly. Because if you open a file, okay, you load lots of information about the file, such as the protection, okay, length of the file, and the most importantly, see this one read. Where does this read the data? It reads from the current position, right? Current index. So what is the current index? Okay, this one doesn't read it from the beginning of the file, right? This one reads wherever my last read left off. Okay, so I need to keep that information at least. I need to keep that information. So you open a file, you load lots of attribute information like the protections and the current index and etc. And you keep them in your memory. And when you say read or write, you use that information in your memory. That's why, okay, the memory means that it's resource, right? It has to be managed. That's why there is a limit in the number of files. You cannot open millions of files at the same time. The operating system will tell you that, no, I cannot open this many files because each one means that it's a memory. Okay, I cannot keep that kind of files. Okay, that many number of files. So you need to open it from time to time. Close means what? Close means get rid of that information that I was keeping about that file. Okay, so we are going to see what kind of information we keep in our memory for an open file. Okay, good. There is a simple program, C program, for what? For copying a file from another file. These are her headers, very simple one. Buffer size is 4 kilobytes. An output mode means that the user is going to have read, write, execute permissions to defines in there. There is the main function. I have the input file descriptor, output file descriptor, read count and write count, and okay, this is a character of a buffer of characters of buff size. If the number of arguments is not 3, that means that, okay, copy source destination 1, 2, 3 parameters. Okay, if the number of parameters is not 3, then I am exiting. This is not good. Okay, what I do here, I open a file as a read only. This is the argument number 1. If I can open it, my file descriptor should be a positive number. If it is less than 0, then I terminate. Okay, for the output file I created, because I'm going to do that way. Okay, so I'm going to create it. If there is an error, I will exit. What could be the possible problems for opening a file? The file may not be there, right? The file may not exist, or I may not have the enough. I may not have the permission to open the file for creating again similar stuff. Okay, and there is a loop, and I think yeah, okay, the next slide has this complete loop in there. There is a while loop in an infinite loop. I think this is the whole loop here. I don't know why this if is not correctly indented. It should be pushed a little bit like that. Okay, so I read the file uh, in file descriptor to the buffer of 4 kilobyte and buffer size. If read count is less than or equal to 0, that means that I cannot read it. There is a problem with the file. I don't know what. So I don't care actually, maybe. Or I'm going to take care of it later. This means that if read count is less than or equal to 0, maybe I reach the end of the file or there is an error. I will break this loop. and write count is, okay, write to the output file from this buffer, but write this many bytes. How many bytes? How many bytes I read from the file? I am going to write it to there. Okay. Of course, this read count cannot be 0 or less than 0, but if read count is 0 or less than 0, then I'm going to exit. Okay. And at the end, when I break, I close my files and I close my files. And if read count is 0, then exit 0, because last read should be 0. If the last read is not 0, that means that it is less than 0. In that case, I will say there is an error while I am reading it. What could be the problem while I am reading from the file? I mean, why would I return an error from this read function? Tell me a case where I would get an error while I am reading a file. It cannot be out of this space because I am reading it.
File cannot be opened successfully.
Well, if the file cannot be opened successfully, in that case, I have already exited, right? I did that. I know that the file is opened successfully, but when I try to read it, I am getting an error code.
End of file, maybe.
End of file means that it is 0, okay? When you get a 0 from a read function, that means that it's end of file, but this one is returning less than 0. End of file is not an error, okay? Negative is an error.
Reading after the end of file, still reading after the end of file.
Well, it's the same thing. You will get 0 again.
Maybe signal interaction. Focus.
What do you mean? I didn't set up any signals.
Maybe this process is working and some signals sent this process and this process is interrupted.
If the process is interrupted, then when it continues. I wouldn't know if the process is interrupted. That wouldn't cause any errors from the read function. As a regular user, I wouldn't know if I am interrupted or not. So what is the reason? What would be a reason for read function?
Maybe the file's size is lesser than the buffer size.
Well, in that case, the read count would be smaller than the buffer size. Between 0 times the buffer size. That's what I'm saying.
File descriptor is that descriptor. Maybe.
Yeah, it could be. Yeah, that could be. So I'm giving a file descriptor that is not valid. I don't have such a file descriptor. You close the file and you are trying to read it again. That could be one thing. Or somebody else moved the file away. Or if I am reading the file from a USB drive, okay, if somebody removed the USB drive, how can I read it? Or if I am reading the file from a network drive, if the network connection is lost, how can I read it? Or disks are mechanical devices, right? If there is a mechanical problem with my disk while I'm reading it, it might return a error code, okay? Or if my file is corrupted. Remember, for me, this is how the file is seen, okay? Sequence of bytes. When I say read, it reads sequentially. That's what I am thinking of. But in fact, this one is stored on my tracks and sectors on my disk drive. And if some of the sectors are bad, cannot be read, but at the beginning of the file they are right, correct, then I can start nicely reading the file, but I cannot continue because some of the sectors are bad. Okay, so these are some of the problems that can happen with the read. So we are always careful about how we handle these. Okay, I think I'm out of my time. Let me take 10 minutes of break. We will be here around 11:38 and we will continue our discussion on the files. 10 minutes of break. Okay, so this is a very simple program, you already know about it. So how many system calls we had here? We made a system call open. Okay, so what do you think open is doing? Open is doing something like finds the file and opens it, and in the memory there is a file descriptor, a file descriptor number 1, then number 2. Okay, it goes like that, and there is a file descriptor table, okay, and this file descriptor table says that, okay, the file descriptor number 1 points to here, number 2 points to there, number 3 maybe points to there, right? So it's an integer. So you index into this file descriptor, and you find your, maybe inside the file descriptor, maybe inside the file descriptor you find your file name. I don't know why I'm writing this thick, but I think my pen is so thick. Because anyway, okay. Your file name, maybe the permissions in there. Okay, permissions. And what else? The length of the file. Tell me something else that I need to put in this file descriptor. Very important thing. Very important thing in the file descriptor.
Path of the file.
Length of the, you mean
File permissions.
I said that permissions, length, file name, I already write it here.
The index.
Index, exactly. Or the current position. Index or the current position. Okay. I need to update this index after each read or write, or after seek operation. So open opens it, and every time I read a file or write to a file, I need to provide this descriptor so the operating system knows if I'm doing the right thing, if I have enough permission to read from it, write to it, and etc. Okay, good. So as we said before, directories are files, but they are special files. In them, okay, in them they keep information about the other files. Okay, so we like this directory structure because it makes the life of a user practical, easier, if you organize your files into directories. Okay, and directories are organized this way. There's a root directory, and under the root directory there might be files, regular files, or other directories. At the beginning of the operating systems, there was only a single root directory, and that was it. I mean, you are allowed to have only a single directory, that's the root directory. So all the files are stored next to each other like that, okay? So whenever you need to find something, you need to look at this root directory, and that's it. That was it. Early personal computers, or the early computers, very large computers, are designed that way because they didn't have many files to begin with. But those days are gone. We don't have such simple structures anymore. Nowadays we have these kind of files. Okay, but there is a root directory, and within the root directory there are other directory for a user A, directory for user B, and directory for user C. Another user C's directory, there is another directory, a file, another directory, another directory. So this is a very powerful structure mechanism. It is easy to find your files, organize them, add more files, make a search, and etc. Okay, on this simple computer, I have maybe more than 10,000 files, maybe 100,000 files. I don't know. Okay, but it is easy for me to find a file that I placed somewhere. Because why? Because I say that file must be under my video files. that file must be my under image files or the class files and etc. Okay, so this is how I organize stuff on my desk, and hierarchical directory systems work this way, and this is the accepted norm. Okay, all operating systems currently use this kind of hierarchy. Okay, but then I mean, giving just a name for a file is not enough. You need to specify the path, right? Okay, for the path there are two ways of doing it. One is an absolute path. Absolute path. Come on. Okay, one is an absolute path, the other one is relative path. What is an absolute path? With the absolute path, this is what you do. Okay, for Unix, you will say from the root directory there is maybe use this one. From the root directory there is C, under C there is another C. Okay, and these file names and directory names are so stupid. Let's say, okay, let me do this way. B1, B2, B3, B1, C1, C2, C3, C4, maybe, yeah, again the same. C1 and C2, 1, 2, 1, 2. I do it that way because in the same directory you cannot have two files having the same name. So let me do it this way then. Under C there is a directory named C1. Under C1 there is a directory named C2. Under C2 there is a file named C1. So this is an absolute path for this file C1. You start from the beginning, okay, and you put your directories one after the other one, and you reach the final one. Okay, so this is absolute path name. Absolute path names are nice, but sometimes they are very difficult to use because with modern operating systems, usually the level of hierarchies is very large. Sometimes you have more than 10 levels of hierarchy. So what are we going to do? Every time I need to open a file or need to refer to a file, am I going to write everything there? No. In that case, I would use something like relative file. What's a relative file? Relative file path name. Relative file path name is this. Okay. When I say list user source, I don't have anything. Has been ls. No, I don't have anything like that. No. Let's try something. B, C. Come on. Yes, okay. Okay, something. So I am saying that okay, when I do this, I am saying that list this file for me using the absolute path name because I am specifying everything. But if I say ls test dot, is that okay? If I do this, I am not giving the absolute path name because I am saying that there is an environment variable named current directory. Okay, my current directory address is this. Okay, my current directory my current directory absolute path is this: home, my username, and the cpp test. Okay, so when I say, without giving absolute path, when I say ls, okay, it said that okay, I'm going to list the current directory. So this is the current directory here. When I say ls test.s, it says that okay, I am going to look test.s under home, accul, and cpp test. Okay, so that's the relative path names, and it is more convenient most of the time. You don't have to specify that large absolute path. Okay, but how do I talk about the other directories in using the relative path? You say, when you say cd dot dot, it means that I need to go to the one level up. So if I do that, now my current directory is this. If I do even one more, my current directory becomes this. Okay, so this is called relative path, and it is used a lot. You could use the relative paths for opening files or doing these kind of file operations. And this kind of stuff is valid for many operating systems. Here is an example. There is a root directory. Under the root directory, I have 5 other directories. And it looks like under the user directory, there are many other directories, AST, gem, and lib. And under gem, there is another one, etc. Okay. For Windows, you usually use the backslash to separate the directories from each other. For Unix, it is the regular slash. For Multics, it looks like they are using this angled bracket sign, or greater than sign, whatever we call it. Okay, so absolute path and relative path are defined like that, and I bet you already know about this. Okay, good. So directory operation, what did we say? Directories are files, but they are special files. So you create them, you delete them, you open them, you close them, etc. So that's how you do these kind of operations. There are 2 special operations regarding the directories and general files already. Actually, this linking and unlinking could be done for regular files too. Okay, linking and unlinking. So linking means this. Linking means this. If I do this, yeah, okay. I might say that under this directory A, I am linking this file C1. So this file C1 is under this C1, and it is also under this A because there is a link. This is not copying, okay? I did not copy. If I copied it, it would have been like this, C1. I did not copy it. I just made a link. This is called linking. And linking could be done for regular files, non-directory files, or for directories too. So linking and unlinking is not specific for directories only. Okay, so you may have used this linking explicitly, or maybe you did not use it before, but there are 2 types of linking options. For many operating systems, this is all valid. Okay, one is the hard link, the other one is the symbolic link. Okay, hard link or symbolic link. So let me talk about this hard link. How do you keep a directory? Okay, you keep information about your, let's say this is my root directory. You say that under my root directory, okay, there is this sr source directory, source, binary directory, user directory, devices directory, and maybe tmp directory. Okay, so these are my files under this root directory. Source directory is another directory. Okay, these are all directories. Or maybe there is a, at the beginning of the file, there is a, for example, I don't know why, but I have this test.c. This is a regular file. So the first five is a directory, the first five are directories, the last one is a file, regular file. So the point I am trying to make is here is this. When you when you take an ls in this root directory, it lists all the files for you. It says that these are the files, these are the directories. How about this directory? This directory is a link to another directory. Okay, like that. And this one is a link to another directory on the desk. And this one is a link to a file, a linear space in the desk. So there is a linking going on in these tables. Okay, so let's look at this bin directory. Inside the bin directory, again you have inside the bin directory you have, for example, D1, D2, D3. These are all directories, and there is another file, a.c, and it's a file. This file could point to the same file that this root directory is pointing to. Okay, so you are seeing this file, whatever it is. Okay, inside this file there is a C program. You are seeing this file. Under these two directories. One is the root directory, the other one is the bin directory. It is the same file. I'm not talking about the copy. It is the exact same file, and I am seeing this file under two different directories. This is called hard linking. This is called hard linking, and hard linking is defined. It creates a link from the existing file to the name specified by the path. Okay, so you are saying that I am going to use the same index number in two places. What is the index number of that file? I am going to use in two places, and it's going to be a hard link. So what is the way to create a hard link in Unix? It is a command ln. Okay, ln works with these options: source and destination. Where is my manual for the ln? Okay, target and link name. Target and the link name. So that's how it works. So let me make ln, my target is going to be, or let me go to my, okay, test cpp. Come on, I hate this sound. cd test cpp, or test, instead of making that stupid thing. Okay, cd cpp test. Okay, so if I do this, these are my files. So I am going to make a link to the sil.txt in the upper directory here. Okay, so when I say ls, as you see, sil.txt is here now. But sil.txt is not here because it is shared. Okay, when I say, okay, this one is not, this is exactly the same as the sil.txt in my upper directory. Am I back? Okay, I am back, right? Okay, you hear me. So when I say list me the details of the seal.txt in the upper directory, it is exactly the same thing, same size. Okay, let me do this stupid experiment. I am going to append everything to seal.txt in my current directory, and if I list ls minus al seal.txt, so its size has increased. How about the seal.txt in my upper directory? It is again same thing. So this is called hard linking. So whatever I do to one of these files, it is exactly happening to the other one, and it looks like there is no difference between them. It looks like it's a regular file because I am using the exact index on the desk. So we like hard linking because instead of copying stuff around, we use the operating system's index to point to the same data structure on my file. This is called hard linking. But the thing is this. I cannot use this hard linking between two different file systems. Okay? So remember, if this one is if this address is 123, okay, if this 100 is 507, I would put here, okay, 507 here too. So these are both showing the same index, so I can find it. But what happens if I like to link a file from a different file system? Okay, one of my files is on my USB disk, but I like to link it to my hard drive. Since they are two different file systems, these two numbers are not valid from each other. Okay, one of them has its own address system, the other one has its own address system. That's why they invented that's why they have invented this soft linking option. Instead of hard linking, there is this soft linking, symbolic linking. Okay, having two names point to the same internal data structure representing a file. A name can be created that points to a tiny file. So I am creating a name, and I am going to create a name, and I am going to create a name, and in that name, a regular file. In that regular file, I will have the link address of the other file. So that's called symbolic linking or soft linking, and it works this way. If I say ln minus, okay, I am saying that create it symbolically and make it this symbolic seal.txt. Now let's look at this stuff. See, as you see, this symbolic seal.txt is pointing to seal.txt, and I can see it, and this is a link file. Conceptually, it is the same thing as the hard linking, but this is a very small file, 10 bytes of file, and inside this 10 bytes, it keeps the absolute address of the other file. Okay, and if I like to do the same thing as, okay, symbolic link. Okay, so keep this in mind. This is 770090, and do that, and see, it is not 90 anymore. Its size has changed. Okay, so that's the advantage of the symbolic linking. So we like symbolic linking better, but what is the problem with symbolic linking? Symbolic linking is more flexible, but what is the problem with symbolic linking? Why don't we use the symbolic links all the time? I mean, why don't we use the hard links all the time? Because hard links are not valid across the boundaries of the different file systems. So what is the problem with symbolic links then? Why don't we use symbolic links all the time? So you guys are not listening, or it's not a difficult question. I don't know what's going on.
Maybe we can miss the original point.
You mean you missed the original point? What do you mean?
So actually in the symbolic link, and we are not creating a direct position of the file, any file.
Yeah.
And we are just pointing. This point, the original. For example, this.
Oh, you mean that
So-
if somebody removes the original file, then your symbolic link.
Our all symbolic links gone. So this causes a problem.
Oh, okay. So let's remove the original one. Okay, I removed it, and this one is still okay. I am going to remove it from the upper directory. Okay, so let's look at this one. Yeah, this one still says that. Oh, okay. This one still is here. Okay. This one is still there, but it is red. My shell is so nice, so I checked it. It say that I am not going to. I cannot find it. It is a symbolic link, but I cannot find the target in there. If I like to find what kind of file is this, say that broken symbolic link, I cannot find it. So exactly what you are saying. So that could be a problem. That's one thing. Okay. Another problem, performance related problem. Performance related problem.
Is it takes long to resolve the link?
Exactly. It takes longer time. Why? Because to find the file itself, you need to open this file first, right? You open the file 10 bytes of file, you read it, you find the address of the other file, and you go there, right? You go there and you open that file, and you find the index of that file, and you follow it. With the hard linking, you don't have it. As soon as you open the file, you have the index. So this is a little bit slower, just a little bit slower. Okay, just a little bit slower.
So I have a question.
Yeah.
So, for example, we created many symbolic links.
Yeah.
We had 3 people, and we opened our unique symbolic links, and we trying to update the files. So what happens? For example, if I write, and when I saved, so someone was writing, he didn't save yet.
Well, it is the same thing as 3 threads are using the same memory location without synchronization. You are causing a race condition. Okay? You wouldn't know the results of it because your result would depend who accessed it first and who write it later. Okay? And that is not in your control, so that's a race condition. So you wouldn't know what's going to come up from that operation. Of course, you will end up with a file. Inside the file, there would be some information, but that doesn't mean that every time you repeat that operation, you are going to end up with the same result. That's the race condition, right? So how do you prevent these kind of race conditions? So you lock your files. You say that this file is locked by somebody. If I lock this file, nobody can write to it. Only you can read it, maybe. Okay. So again, the inter-process communication, mutual exclusion, these kind of stuff are still valid for the file sharing. File sharing is no different than memory sharing.
Sir, I have an example in mind, and I don't know if this is correct. Creating a file in standard Windows and creating a shortcut to it would it be a example to symbolic and hard links?
In Windows, creating a shortcut is a symbolic link, yes. To be able to understand if it's a symbolic link or not, this is what you're gonna do. Let's say, let me open this thing. So on this computer, unfortunately, I have only a single physical device. But if I had another physical device, can I add another physical device to this computer? Let me see if I can find a USB stick. Is this a USB stick? Okay, I found that. There is a USB stick and I am trying to add it. Did I get it? Unfortunately, I don't have enough number of ports on this computer. I am using my dock to add it, but it looks like I cannot. Maybe just okay. Instead of camera, I am going to add okay, so I have a file, I have another one here. So what I'm going to do is I am going to get I'm going to make a shortcut, and I think it's going to go to the desktop, right? It is going to on the desktop. Where is it? Yeah, okay. So I get it, and I am going to paste it here. So symbolic this happened. If I click on this, as you see, this file is being opened, right? So I was able to make a symbolic link across the different file system boundaries, because the file system for my USB stick is very different from the file system of my hard disk. They are very, very different. Okay. So symbolic links is the same as the in Windows world, same as the shortcut. Okay, and you can use you can use the linking for both directories and the files. Okay, good. Any other questions?
I have another question.
Sure.
For example, in the original file, so we had no permissions. So we created a symbolic links to different directory. Can we have an access if we cannot have an access to the original file?
Of course you cannot. No.
So I mean, I can modify the file whatever I want.
No, you cannot. So you cannot.
So permissions for the original file, right?
Permissions for the original file is still valid. Okay. And by creating a link, symbolic or hard link, you cannot work your way around this protection mechanism. No. Okay, good. So let's look at this file system implementation idea. So far we didn't talk much about the file system implementation. We looked at the stuff like our users, like we are users, like these are the operations for directories, etc. But from time to time I try to go internals like these index numbers and etc. Now we are going to look at this file system implementation. Depends on the file system again. Okay, so we are as users we are concerned about what are the valid file names so that we can pick valid file names, nice file names. Okay, what kind of operations can I do with the files, like opening a file, creating a file, etc. Okay, usually you open a file and you use it. Nobody will ask you why are you opening a file, right? I ask you that because I was going to go into details of opening a file. Okay, and so we look at the directory structures like these. These are the user's view of the file system. But when it comes to implementation of the file systems, when it comes to implementation of the operating system, okay, we are interested in how files and directories are stored on the secondary storage, okay, how the disk space is managed, okay, how do I keep my free space or the occupied space, okay, and the most importantly, maybe how do I do all of these operations in more reliable and efficient way. It has to be reliable because the main idea of secondary storage is my data should, okay, my data should be kept in a safe place for a long period of time, okay, not like my main memory. Also, I should do everything in more efficient way because, as we said before, doing a disk operation, secondary storage operation is much, much, much longer than doing it in the memory. Doing it more in the memory. So let's look at the details of the file systems with these things in mind. Maybe it would help us to look at the real data, how it is organized on the disk. Okay, as you remember, our disks are organized into tracks and the sectors. Okay, each sector has a number, and sector 0 is a special place. Okay, it's called master boot record. Let's say I have a single disk on my computer. When my computer boots up, okay, sector 0 is the place where I read my original operating system. Okay, so the BIOS, the basic input output system that is first loaded in my computer from my read-only memory, it reads the sector 0 of the hard disk, or if you have a floppy connected, floppy disk, whatever it is, okay, and there is a small program there, and that small program starts running. So that becomes your, after the BIOS, that becomes your first operating system. It has full control of the computer. It's a very simple, very basic operating system, but it is the first operating system. Okay. At the end of the master boot record, there is a partition table. What's a partition table? Let me show you this. Okay. So this is your sector number 0, master boot record. This is sector 0. So this one contains the original operating system. Very simple operating system. Its task is just to load the real operating system. At the end of this master boot record, there is a partition table. Partition table is this. It says that partition table, as the name implies, is a table. It says that part 1 on this disk, okay, is an NTFS file system, and it starts at at this address. Its length is this much. Okay, partition 2 is a, let's say, FAT32 file system. It starts at 20,000 and it continues for 10,000 again. So these are the rest of the disk is the disk partitions, and each disk partition could have a different. Disk partition could have a different file system on it. They don't have to use the same file system information. Okay, and one of the partitions are marked as system partition. Okay, in this case, my second partition, okay, this is my first partition point here, and this is my second partition here. My second partition is my system partition. So the code in the MBR finds this partition and it loads the first block of that partition into memory, and this one becomes your operating system. Okay, this is the initial code for your operating system. And depending on the file system, the structure changes. It looks like this one has a Unix type file system because it keeps inodes and etc. Okay, but at the beginning of this one there is this operating system code. So there are two types of temporary operating system that you load at the beginning. You first load your BIOS, which is not on the disk, it is on the read-only memory. Okay, BIOS. You read it in your memory and you execute your BIOS. The task of the BIOS is to identify your hard drives and etc., your amount of memory, all kind of stuff. After that, it goes to the sector 0 of the hard disk, okay, and it loads this MBR. MBR is responsible for finding the active partition, system partition, and loading it. After it is loaded, the boot block takes care of all of your computer. Now it is your operating system. So it is very important to keep your BIOS and the MBR very, very safe, because if some people with the bad intentions had an access to your BIOS or the MBR, they can load up their own operating system, right, without you knowing. That would be a bad thing. Okay, it looks like I am out of my time for today. Tomorrow we are going to do only a single hour of lecture. Okay, just 1 hour, because we have the graduation project presentations in our second hour. So it will be just a 1 hour lecture. It will be our first lecture then. Any questions for today's lecture? Any questions?
Thank you, sir.
There is a guy on YouTube, there is a YouTube channel. He is he's teaching you how to write your Linux kernel. He had a series first, he said that you write your own operating system. And nowadays, I think he is doing it, write your own Linux kernel in a very simple terms. I suggest you follow that guy. I forgot his name, but I think I will remember. If I remember it, I will post it tomorrow. He always keeps talking about these kind of low-level details. So, I mean, when he says that write your own Linux operating system, he assumes that you know the general concepts of the operating system, how to design an operating system, how to think about the threads and the processes and the file systems and etc. He's talking about the mechanisms of writing operating system. Okay, the low level stuff. So after you know the high level stuff which we are teaching, that would be a very nice activity for you to learn the low level stuff for Linux. So try to watch that video, series of videos actually. It is simple to follow.
Sure, I think I found it.
Okay, what is the name of the guy?
So actually there is no name. Write your own operating system.
Good. Okay, so that was the old one. Okay, so he's doing the Linux kernel right now. So could you paste it to the chat? to the chat
Yeah,
window?
of course.
You pasted it?
Yeah, I did.
You did? Okay, that's good. Okay, thank you.
Okay, no problem.
Okay, good. Okay, I'll see you tomorrow. So I had many people saying stuff in my chat window. I don't read chat windows. No need to shift the memory in case of new data. Signal raising. Okay. Okay, I'll see you tomorrow. Bye.
Bye.